In video 20C, we talk about the material properties from bonds, energies, and structures. So first, let's consider the nanostructure of a material. So we consider the material being made up of bonds that can stretch, and we see here there are these black lines that have length R naught. That is that equilibrium bond length. And we call the anchor points of multiple bonds nodes. That's these circles in this figure. Now we'll use an idealized cubic node geometry to calculate information about stress and strain of the material. So considering the bond that I showed in red, anchored by this node shown in blue, and let's ask, what is the cross-sectional area used up by that bond in the material? So if it's anchored at this blue node, it's coming in and out of the plane, so the cross-sectional geometry is in the plane we draw. So let's assign the rest of this box to the lower left of it to that node, just as we could assign this area to this bond ending in the green node, and this area to the bond ending in the red node, etc. And in this way, each bond is then assigned to this little square that has dimensions R naught by R naught. That is, the cross-sectional area per bond is R naught squared. We can use that then to calculate the stress per unit area. So the stress is just divided by the force divided by the cross-sectional area. And the force is the derivative of the energy function, and the cross-sectional area is R naught squared. So now next we want to have an expression for strain. Because strain is the fractional stretch across the bonds, that means strain is simply the difference between the actual bond length and the equilibrium bond length. And to make it fractional, we divide by R naught. So we can then combine these to relate stress and strain. We've already defined the Young's modulus as the ratio of stress and strain within the linear region. And so then we plug in the values that we just calculated above. So the stress is this value. So we have the derivative of the energy function divided by R naught. And then to divide by the strain, we will invert this, which we have here. Then looking at that, we see we can cancel the R naught with one of the R naughts there, getting rid of the squared sign, leaving us with the derivative of the energy function divided by the R naught times the difference between R and R naught. Now, to continue to simplify this expression, let's remember several properties of the energy function. The energy function is, we determined, the energy at the equilibrium bond length plus 1/2 the spring constant times the square of the difference in length from the equilibrium bond length. So if we take the derivative of the energy function from that, we just get the K times the displacement of the bond. And that makes sense. This is a spring constant, so we've just said, and remember that du dr, that's the force, is the spring constant times the bond, which is intuitive. So if we plug this into what we just derived, then we replace this with that force times the displacement. But since we have this expression for the displacement on the top and bottom, they can cancel, and we're just left with the Young's modulus is the spring constant divided by the equilibrium bond length. Now, there are some limitations to this derivation. We assumed a perfect crystalline lattice, but most materials have other lattices, so the bond area is not exactly R naught squared, that is the equilibrium bond length squared. And also, bonds are not all the same. So materials often have different types of bonds. And if that's the case, it's the weakest of the bonds that's the primary determinant of the Young's modulus. So for these reasons, all these calculations are only accurate within maybe twofold. This may sound really lousy. Twofold accuracy sounds terrible until you remember that a lot of the materials we're looking at can alter in or can vary in Young's modulus over 6 or more orders of magnitude. So twofold actually gives you a fairly good idea of the stiffness of the material. And if ever you're making these calculations and you're trying to decide between different choices and your answer has less than a twofold effect, then just remember those choices just don't matter. You're trying to get an estimate. You'll see that example come up in the homework. So finally, we'll apply this idea to the example of the material we looked at previously to ask what is the Young's modulus of a material that has that energy function that that's the difference of these two exponential terms that we looked at before that we see in this equation here. So we learned that the equilibrium bond length is d times the natural log of 2, and we learned that the spring constant is c over 2d squared. So to calculate the Young's modulus, we just take that ratio, and then we simplify. So bringing over these values, we have the c over 2d squared was the kappa, was the spring constant, and then 1 over this d times 2 natural log of 2 was the r naught. We just combine those, we get c over d cubed multiplied by this cofactor. So again, we'll want to do an energy check. C is an energy, that is joules or Newton meters. And and then D, of course, is in meters. And so we have, oops, that should be a cubed there. We have Newton sine meters divided by meters squared, where cubed is just newtons per meter squared, or Pascal. Check, that is what we want for the Young's modulus. So that's another example of this, using just the math. In our lecture, we'll apply this to many more examples to actually explore real types of material and understand why salts or ceramics and metals and a number of other materials have very different Young's moduli.